so last time we were talking a bit about CDMA. We did, we basically got to the point where we were explaining how to get spreading code. So what are spreading, chip sequences. So in CDMA, the basic idea is we have a single user will have a binary transmission, so a single user will have signals S0 and S1 as usual, but these are formed in an unusual way. So S0, in order to get S0, we have first what we call a chip C0K, and also C1 of K, which is equal to minus C0K. So we call these chips, and basically what we do in order to get these modulation functions is we string together a series of chips. So for instance, we'll have a chip sequence, let's say 0, 1, 0, 0, 1. And basically, we form S0 by substituting each digit with the appropriate chip. So we would start with C0, C1, C0, C0, C1. And then we're going to say S1 is minus S0. So really, it's a bit is sent by selecting either S0 or S1, but in another sense, I mean, each of the chips can be thought of as a bit, so each bit is just represented by a sequence of sort of sub-bits. So for that reason, sometimes we call the chip sequence a code. So in other words, this sequence of bits, or this code word, represents a 0, and the opposite of that, so minus S0, minus, because of the equivalence between 1 and plus and 0 and minus, the code representing 1 would be just the inversion of all these bits. Okay, another point, we call this spread spectrum. Normally, let's take this particular case. So this, in this case, let's call the length of the chip sequence LC. So that's LC. Then we string together LC chips in order to get a bit. The chip time, the amount of time we spend sending a chip, let's call that TC. So that's the duration of a chip. So, I mean, every TC seconds, we could potentially be using these chip waveforms to send a different bit. So for that reason, the bandwidth of spread spectrum is measured with respect to TC. So we've said before that the bandwidth is roughly proportional to the bit time. So in this case, a bit is assembled from a code word of several sub-bits. So each of these we could make some arbitrary value, but we choose not to. Instead, we choose to string together this sort of code word of several bits in order to create S0. So think of it another way. The bandwidth is roughly proportional to the fastest rate at which things change in the signal. So where are things changing in the signal? They're actually changing at the chip level. So the speed at which the chips change is 1 over TC. So we're going to say bandwidth. Bandwidth of this spread spectrum signal is 2 over TC. But TC is equal to, well, actually it's better to think of it this way. the bit time is equal to, well, how much time do we take to send a bit? Each of these chips takes TC seconds, and we have LC of them. So therefore the bit time is LC times TC. So in other words, TC is equal to TB over LC. If I substitute that in back up here, I get 2 LC over TB. Whereas usually, and again, this comes up because, simply because I'm taking each of these bits, and instead of transmitting them as one particular function, I'm transmitting them as a sequence of sub-bits. But usually, if I for instance, in polar NRZ or BPSK or something like that, where I only have one signal that I'm using, usually I've said we're going to use B equal to 2 over the bit time. So in fact, that's where this comes from. It's because the chip time is now the new bit time. The chip time is the rate at which things are changing in the signal. So in other words, CDMA uses LC times as much bandwidth. LC times the bandwidth. That's why we call it spread spectrum. So basically what we're doing is we're taking a signal that would normally fit in some bandwidth, say this is 2 over TB, and we're applying this chip sequence and spreading it out over 2 over TB times LC. That's why we call it spread spectrum, because normally this signal, which would occupy a small bandwidth, is being expanded over a huge bandwidth. So this also tells you we can also, so basically the idea is the LC is chosen to expand the signal to occupy the available bandwidth, all available bandwidth. So you can imagine why. LC gives you the length of the chip sequence. What we want is we want chip sequences that are not orthogonal. Again, we don't want orthogonality because we know that orthogonality breaks down if things aren't synchronized. But what we want is LC long enough so that we can get signals that are roughly orthogonal. And it turns out that that property improves as LC increases. So basically, expanding over the entire bandwidth is a feature. What do we want to do here? Basically, we want to choose LC to expand the signals to occupy all available bandwidth. So for instance, let's say the available bandwidth is 1 megahertz. And let's say I want to send data, desired data rate is 10 to the 4th power bits per second. What does that mean? TB would be equal to 1 over 10 to the 4, which is 10 to the minus 4 seconds per bit. So the nominal bandwidth would be 2 over TB,